All right, today we're going to go on a mission to crack the code of algebra. Yeah, I know, it can totally look like some kind of secret language, right? But I promise you, by the end of this, you're going to see it's just a bunch of puzzles. And you're about to become the detective.
You know that feeling, right? You're staring at a page full of numbers and letters, and it just feels like everyone else got a secret decoder ring but you. Well, guess what? Today, you get the ring. We're not going to treat these problems like chores, but as mysteries we're going to solve together.
Okay, here's our first clue. We've got a table showing the connection between pears and figs in different baskets. Just look at the numbers. When there's one pear, there are 2 figs. When you have 3 pears, you've got 6 figs. What's the hidden rule here? Don't even worry about the answer just yet. The first step is always just to look for the pattern.
To solve any puzzle, first you got to identify the key players. Now in algebra, we call these players quantities or variables. One of them is the leader, and the other one follows. Figuring out which is which, well, that's the first major clue to cracking the whole code.
So, first up is the independent quantity. The easiest way to think about this is as the cause. It's the number you start with, the one you're in control of. Like if you're buying pizza, the number of slices you decide to buy, that's independent. On a graph, this is pretty much always your horizontal line, the x-axis.
And where there's a cause, there's always an effect. And that's our dependent quantity. Its value completely depends on whatever the independent one was. So if you buy 3 slices of pizza, the total cost totally depends on that number, right? The cost is dependent. And on a graph, that's your vertical line, the y-axis.
And what's so cool here is that the table and the graph, they're telling the exact same story, just in different ways. Look at the X column in the table, 8, 12, 16, 24. Now look over at the graph's horizontal line. See? Same numbers. And the Y column, 2, 3, 4, 6, it perfectly matches the vertical axis. They are just 2 different ways of organizing the exact same set of clues.
All right, so now that we know our key players, the independent and the dependent quantities, we need to figure out how they're connected. And in this world of linear relationships, there are really 2 main secret pathways that link them together.
This is so important. This slide breaks down those 2 main pathways. First, you've got additive relationships. This is where you always add the same number. The equation for this is usually going to look something like y equals x plus b. Now, on a graph, its line will not pass through that 0 point, the origin. Then we have multiplicative relationships. This is where you always multiply by the same number. Its equation looks like y equals kx. And its graph? It's always a straight line that goes right through that origin point, 0, 0. That's a huge giveaway.
Let's look at a real example. So here we have Gabriella's age and her mother's age. Let's test it out. Could it be multiplicative? Is 3 times some number 30? Yeah, times 10. But does that rule stick? Is 5 times 10 equal to 32? Nope. Okay, so let's try an additive rule. How do you get from 3 to 30? You add 27. Let's see if that's our pattern. 5 plus 27 is 32. Yes. 9 plus 27 is 36. Perfect. It's an additive pattern. We found it.
Now, let's check this one out. Calories in bread. Let's try addition first, just to be sure. 2 plus what? 138 is 140? Okay, so does 4 plus 138 equal 280? Not even close. So let's try multiplication. How do we get from 2 to 140? We multiply by 70. Now let's see if that's our secret rule. 4 times 70? Yep, 280. 6 times 70 is 420. We've cracked it. It's definitely a multiplicative pattern.
Okay, finding the pattern is a huge win, seriously. But a true codebreaker needs to write down that secret rule in its official language. So it's time to turn our pattern into an actual equation.
So how do we actually make that jump? This slide shows an awesome tool, the process column. It's that middle column that basically helps you write down what you're thinking. For one tricycle, the process is 1 times 3. For 2 tricycles, it's 2 times 3. Once you see that, you can write the general rule for any number of tricycles, which we're calling t. The process is always t times 3, and that gives you the number of wheels, w. And just like that, there's our formula. W equals 3 times t.
So really, it all just boils down to this simple 3-step mission. First, you identify your cause and your effect. Second, you test the pattern. Are we adding or are we multiplying here? And third, you write the rule down as an equation. That's it. That's how you officially crack the code.
All right, now that we have the tools, let's see how this all comes together. One of the absolute coolest things about algebra is that you can tell the exact same mathematical story in 4 totally different ways: a verbal description, a table, an equation, and a graph.
So it almost always starts with a story, right? A story told in words, the verbal description. This gives us all our clues. In this case, we know we're dealing with the number of books and the total cost. Next up, we organize that story into a table. So if 6 books cost $45, a little bit of division tells us 1 book must cost $7.50. And from there, we can easily fill out the rest of the values. And suddenly, the pattern is just so much clearer.
Now, for the equation, this is the secret formula in its purest form. It tells us that the cost, C, is always going to be equal to 750 times the number of books, B. It's really the most concise and powerful way to describe this whole relationship.
And finally, the graph, which turns all those numbers into a picture. Each pair of values from our table becomes a single point on the graph. Connect the dots, and what do you see? A perfect straight line going right through the origin. And remember what that means? That's our visual proof that we're dealing with a constant multiplicative relationship. It all connects.
Now listen, even the best code breakers fall into traps sometimes. But mastering the code isn't about never making a mistake. It's about learning to spot the common traps ahead of time so you can just sidestep them. So here are the big ones to watch out for. First, mixing up additive and multiplicative rules. That's why we always test for both. Another big one is getting your independent and dependent quantities backwards. Just remember, cause and effect. A classic trap is swapping x and y when you're plotting points on a graph. And finally, simple little mistakes, like seeing a ×2 pattern but accidentally writing +2. Honestly, just knowing these exist is half the battle. So, if you take one thing away from all of this, let it be this right here. The goal isn't just to get the right number at the end. The real goal, the real power, comes from looking at a situation and actually understanding the story of how things are connected. That's what cracking the code is really all about.
So I'm going to leave you with a final thought. Math isn't just stuck in textbooks. It is everywhere. I mean, the cost of your groceries, the time it takes to get to a friend's house, the data plan on your phone, it's all patterns. So what hidden patterns, what secret codes can you find and decode in the world around you?